Assalamu alaikum dear students. The course title is Advanced Theory and Computation. Today is week 4 and lecture number 2. As you remember from the previous lectures, we have already studied descriptive definition of languages, recursive definition of languages, regular expression, and now method 4, that is the finite automata, right? So what is finite automata? Finite automata is a representation of mathematical modeling of computer sciences, right? So whenever we have some kind of work or proposed work in your research or your programming, so you need to design some graphical view. So for that representation, we have the finite automata, right? Another definition of the finite automata, that is the abstract machine. What is abstract machine? Abstract machine actually it's a graphical mode or graphical representation. Like for example, we have admission system in Sarojini University. So first of all, the student come to the admission office, collect the form, back to home, fill the form, attach all the required documents, and come back to the admission office of Sarhad University. Right? At Sarhad University, they check the documents. After completion, the procedure, they forward their set of documents to the faculty. The faculty call the student for interview and check with different requirement. If the student fulfill the requirement, then it may allow for the admission. So this is the graphical representation. If we put it in data flow diagram or any kind of diagrammatical mode, this is called finite automata, right? In finite automata, we have some kind of states. What is state? Like for example, you come from home to university or admission office. So you come actually from state 1 to state 2, right? So this is called state. And the distance or the line between your home and the admission office of Sarojini University, this is called transition, okay? Like for example, I say, give the name your home to the Sarojini University admission office. So what could be the name? So you say this is the route to Sarhad University of admission office. So this is called transition. Okay. So this is the finite automata. Further, we have some formal definition of the finite automata. Like in finite automata, we have number of states. Like in the first point, we have number of states. So what is states? As said at the beginning, at the previous slide. So whenever you go from one point to another point, like if you want to draw a line from point A to point B, so point A and point B, these are the states. Okay, so point A here is the initial state and point B here is the final state. So it depends on the requirement of the question or the pattern of the question. Okay, fine. Second point, we have finite set of input letter. Like in the regular expression, you have seen, like for example, A, B, B, C, holsteric, and so on. So these are called the input states, okay, or the input letters. Okay, it will travel to you from state 1 to state 2 and so on, right? Then we have finite set of transition. Like I said before, if you want to go from point A to point B, so you have to give some name, some label, some tags. Okay, so this is called the transition. Okay, like what I've seen over here, for each state and for each input letter, there's a transition. Okay, for example, if you want to go from point A to point B, so that path you have to define what is the name of that path. You have to put some label, some address, or some tags. Okay, showing how to move from state 1 to state 2 or another state. Okay, so whenever you want to go from state 1 to state B for state to any state, you have to define some logic for that. Okay, so this is actually the preliminary requirement for designing the finite automata. Like you have to mention the states. Okay, then you have some input values coming from the data set, and then you have some transition. If you go to between or among state, you have to define the logic, the condition, the pattern. Okay, like we have a very practical example for finite automata. We have an example like we have the style. Like we have example of turnstile is two possible state that could be logged and unlocked. What is the turnstile? Turnstile is the like for example you are using the BRT bus services. For that you have to enter to access the bus services. So there's a logic there's a gate, okay, not a security gate but there's a payment gate. Okay, so that payment gate by default is locked. Whenever you put the card of zoo, so that is open. So that is open. It is the barcode of that card, right? So they actually read the station. Like for example, you are going from the university town. You are going from the semi college bus station, right? So they read the money. You have sufficient amount, and they state that you are going from bus station X. Okay. So that is the lock condition. And what is the unlock condition? The unlock condition is that whenever you are leaving from BRT station and you put it again the card on the exit of that station, so they charge the amount or they charge the money or they charge the coin. So this is the unlock state. Okay, so this is the example of the lock and unlock regarding to the representation of the finite automata. We have the figure over here, like we have the lock state and unlock state. So for the lock state, whenever you want to go from that state to another state, so there's two possible way. First of all, you have to push. So the push means you have to keep the BRT or zoo card over or on the barcode of that entry gate. Okay, so that will read the money. They say, okay, you have the sufficient amount, like I don't know, it may be maybe 20 rupees, the minimum cost. So they will go to the unlock state, right? So whenever you travel from state 1 to state 2, okay, so you are in the unlock state. So before you are exiting from the BRT station, so you have to place the card, okay. So that will detect the money, the coin mean, and then it will go to the lock state. It means it will allow to you to exit from that gate and it will go to the lock state. So this is the how we represent the finite automata for the practical life example. Okay, further we have some definition over here. It could be also called a directed graph, okay, which is usually called state diagram. Okay, the states, these are the states, okay, state locked and unlocked state, and the arrows are represented over from here to here and here to here. These are a transition, and whenever it is repeated on the same states, this is called loop or looping. Okay, okay. So each state is represented by a node. These are the nodes. States are the nodes. Okay, and the arrow symbols are the edges, or in other words, this is called arrows. Okay, so these are actually allowing you from one state to another state based on some condition. Okay, here we have seen the word trigger. Trigger means whenever it change from one state to another state, is called trigger. It means to perform some action or activate that or activate for that action the states. Okay, so this is called the finite automata, how we can see in our real life example. Further we have the transition table. Okay, so how we can design the transition table for finite automata for lock and unlock gates. Okay, so we have the lock. So in the lock we have two kind of inputs or the data set. Okay, so this is coin and push. Whenever we place the or put the coin, so it will unlock. Okay, so it will unlock, and when we push, so it will become locked when we go inside. Okay, and same for the unlock. So we have the same operation. So we actually use here the exit operations. Okay, this is the okay, dear students. This is the abstract data types, which is the clear definition of the finite automata. Here we have very simple example. Door open and the door close. Okay, so we have the transition of close and we have the transition of open, right, from close to open. So this is the open transition, okay, which is the condition actually, right? And from open to close state, so we have the close condition, right? So what could be the graphical representation? So this is the graphical representation. So what could be the points or what could be the steps involved to perform such open and close of the door? So we send an event. What is event? That is actually the action, okay? Receive the action, like for example over here, so the action could be open, the action could be the closed one, okay? Then we have trigger the action. Trigger mean fire the action actually, okay? So that action based on the requirement, okay? Activate the action and the decision which is open and closed. So this is the abstract representation of how we can define or how we can use the finite automata for graphical representation, okay? So this is very common example. Okay, dear students, then we have some application of the finite automata for hardware and software based, okay? And hardware based application of finite automata we can use for design of digital circuits, okay? Like for example, we can use for programming logic device. Like for example, the logic device, I'm giving an example. Like we have the battery of mobile or we have the battery of laptop. So it will give you the logic through programming to the battery, whether it is the charge is full, whether the charge is not full, or something like that. So this is done with the support of programming logic device using the finite automata state machine. Okay. Second example, we have a programmable logic controller. So usually this kind of programmable logic controller we use inside the microprocessor. Like for example, whenever it receives the some operation from the user, so the microprocessor will decide whether it is arithmetic operation, it is text operation, it is string operation, what kind of operation. So this is done with support of controller logic circuit design. Okay. Third, we have the logic gates. Logic gate we usually use it for true false values. Okay. For different kind of color representation like RGB, green, red, green, blue, right? So we can also use the logic gates as well. One of the examples for finite automata hardware representation base. Okay, and sometimes for logic gates we also need to generate a sound from the hardware instead of from software. So we may also generate using the logic gates. Okay, flip flop, that is the true false off on, okay, 0 1 and so on. So sometimes we need to on, sometimes we need to off. Representation of different colors usually we use for animated graphics. Okay, and the relays means for example you want to reach from point A to point C, so we need a support, so that support which is the point B, so usually called the relay. Okay, like for example your mobile is not receiving the signal from base station A, right, because you're far away. So you are using the antenna, or you have to install the antenna inside your home. So this is called the relay. Maybe you have seen such kind of example. Okay, then we have some software-based applications. The first one we have automata-based programming. I will give an example at the very beginning, like to design the set of ABBA, the whole string. So for that we need the finite automata. Then we have the second example, event-driven finite state machine. Event-driven mean that we have some kind of hardware machine, right? So we are controlling using by some application or some programming or some software. Okay, like for example for the robot. So in the robot we have installed some logic circuits. So that logic has been instructed using by some AI programming, right? So they tell us, for example, pick the glass, drop the glass, bring the glass, and so on. So this is usually done with the event driven. Okay. Then we have virtual finite state machine. Like we can connect many devices virtually without bring them to physically in one place. So we need to connect them in logic in environment. Okay. Then we have a state design pattern. Okay, so state design pattern. Again, we have to design the finite automata for any kind of problem, which accept like sequence of or pattern of double A's, double B's, even numbers, prime numbers, and so on. So this is the example. Okay. Now we have some very basic example before going to the detail of the finite automata. You have to be understand or you have to be very carefully listen these things. Okay. Okay, we have a set of A and B. Okay, then A and B mean these are our inputs. Okay, which will perform some action. Okay, then we have the states. So there are three states X, Y, and Z. So they have given some initial condition. Okay, what is the condition? X is the initial state. Okay, the initial means the starting state. Okay, and Z is the final state. So these are the very important states. Okay, student. So then we have some transition. Transition mean move from one place to another place. Okay, so we have to consider the three states X, Y, Z, and we have to execute or trigger the inputs A and B. Okay, so let's see how we can do using the finite automata. So at the first point we have at state X. Okay, so it will read A. After reading A, so it will directly go to Z. Okay, so this is the one condition. Second, we have at state X, which is the initial state. Okay, it will read B and it will go to Z. Okay, this is another alternate transition or path. Third, we have at state Y, right? It readings A and B and will go to Y. So if we see to this statement, so it is a loop. It repeats itself. It's a recursive statement. Okay. So how we can repeat the recursive or loop inside the finite automata? We will see later in the diagrammatic mode. Okay. 4 point at state Z, reading A and B, and it will go to state Z. So again, this is also a recursive statement. Okay. So further, we have to see how to draw the transition diagram or table. Okay, keep in mind we have the 4 steps. Okay, so how we can design the transition diagram or table? So these are the old state. You have to first write rows and column. Okay, so these are the old states, or you can say states, and these are the transition, the new states. Okay, and these are the input data. A and B, which is I have mentioned over here, reading A and reading B. It's up to you whether you say transition A and transition B, or you just say A and B, or you say reading A and reading B. It's up to you. It's totally optional. Okay. So betterly, I will suggest you. Sorry. So betterly, I will suggest you place over here the transition. Right. This is A and B, which is the input coming from here, coming from set of input, right? And then we have 3 states X, Y, Z. Okay, so A, B, and X, Y, Z. Okay, if we see from here, so we have the minus and the plus. This is the logical symbol. Okay, the minus symbol, it means the starting point or the starting state. Okay, the plus symbol, that is mean the final state. This is the final state. Okay, this is the initial state and this is the final state. Keep in mind, this is very common. Okay, so usually if we do not use the symbols, mean the state name like X, Y, Z, so you can also use the minus and plus symbol. Okay, it's up to you, but usually we prefer the starting symbol, mean the initial symbol, minus, and the final symbol, the plus symbol. Okay, other than this X, Y, Z, we can also say Q0, Q1, Q2, and up to Qn. Okay, so we can also use that one as well. That is depend. Okay, let's come to the point. If you see from here, at state X, it's reading A, and then it reads to state Y. Okay, so initial it is X. Okay, if I read to A, like here, that's like cross way. Okay, so if I read A through X, so it will reach to Z. Okay, And the second point, because we have the same input, the x, okay, so you can repeat it over here as well. So usually we do not repeat to make it more optimized, okay. So this is the x, okay, so it will read b, so it will reach to y, okay. At that point, y, at state y, so I'm at state y, right, at reading a, b, and it will go to, or it will reach to y. So it means I can say a, b. So for, if I read a in this state 3, okay, so it will reach to y, right. At this point again, if I say I'm at state y, right, and I want to read b, and it will reach, it will must reach to y. So like this way, okay. So how we define the loop or recursive language on the same states, okay. Like for z as well, which is the final state, okay. So it will also read a on the z, and also it will also read b on the z, okay. So how we can see in the finite automata for such transition table, okay. Let's see in the next figure. Okay, if we see, if we keep the English statements, and if we keep the transition table, so we can easily know how we can do transition diagram, okay. This is the initial state and this is the final state, okay. So at the beginning I say, right, x at state x, reading a, go to z, okay. So this one, okay, this is the transition, it reached to z, we have read a, okay. Then we have, it will go to b, sorry, read b and reach to y, okay, like this. So again on y state it will read a and b. So this is the looping, this is the recursive, okay. And the same for z as well. So actually we have a different kind of pattern how we can design the transition diagram for finite automata on the given set of data, okay. So this is the real example how we can implement for hardware and software applications. Hopefully you have understand this one, okay. So let's see another example. Okay, before going to the next example, we have over here how we can design the regular expression, okay. So according to the statements over here in and the transition diagram and the transition table, so it is very clearly we have, it will always start with a, and then we have a plus b whole static, okay. Like, okay, this was the condition, it will always start with a, right. Then we have a plus b static, which is optional, so I can read a over here, sorry, from here as well. If I omit this one, if I consider this one, if I do not consider this one as well, okay. Also over here a b, okay. So omit the a option, so we can also reach to b, right. If I reach over here to this z point, so a b I can repeat it from here, okay. From here if I omit a and I reach y, reading a, also reading b, so over here y I can also read a and b using the static portion. So this is how we can use the regular expression, okay. So this is the important thing for finite automata, transition diagram and transition table. But usually in the paper they ask the transition diagram, okay. The transition table in the English statement, this is for your own confirmation whether you have correctly drawn the transition diagram or not. This is up to you, okay, these 2 points, but this is important for transition diagram. Another example we have, the input is a, b, okay. The states are x and y, okay. So what is the condition over here at the beginning, okay. X is both initial and final states, okay. So it means we have like a for loop, if I understand at the very first step over here, okay. So what is the transition? So these are transition, okay. These are the condition you may call. At x state, reading a or b, go to state y, okay. At y, reading a or b and go to x, okay. So this is very simple. Keep in mind the statements over here, a transition diagram. Okay, over here they say x is final in the initial point. This is why in the transition diagram, sorry, in transition table we have placed the plus minus as well. Okay, so over here they say at state x reading a and b and then reach to y. Okay, so here we have y. So if I say I want to read b on this state, so x, if I say state x and reach to y, so it will read b, it will read the b. Okay, if I say I want to reach to y and I want to read to a. Okay, so from here to here, then so it will read the a. Okay, same for y case as well. Okay, if I want to read the b, this b. Okay, so I say start from x from y and end on this point. Okay, second point. Okay, if I want to read the a, so I will say start from y and end it to x, so it will read the a. So this is how we can draw the transition table for double confirmation of the transition diagram. So this is the example according to the statements and according to the transition diagram. Okay, so if earlier I said in this lecture, plus minus we use for final and initial accordingly or respectively. Okay, so over here we have the x and y according to the statement. For x state it read a and b, which is reached to y, so a and b in reached to y, and same or inversely for from y to a, and so on. Okay, students. Okay, so what could be the finite matter for this one? Okay, so this is if we see to the pattern over here, this one and this one, so it represents the E1. Okay, E1 of A's, E1 of B's. Okay, AA, comma BB, AB, right, BABA, and so on. So this is the E1 states. So it shows the E1 base, E1 states for particular expression. Hopefully, students, you have understand this thing. Then we have an example of the same. We have the odd length. Okay, so this is also the odd length. Okay, it depends on you how you can generate the odd length from this one. So what could be the regular expression for this one? Okay, we have example over here. Consider the language L of string. Okay, define our A, B starting with B. Okay, the language may be expressed by a regular expression B, A plus B whole square. It may be expressed by the following finite automata. Okay, so if I see over here, okay, so we have only one final state over here. Okay, and then this one we have the optional one. So if I say over here minus to plus, okay, so it will read the B. Okay, so this is B. Okay, then we have the loop over here. So you can draw the loop over here, right? For A as well, if I say I want to start with A, right, and omit the B, so you may also draw this portion as well. But this is optional case. Okay, this A reading is the optional one. Okay, usually we have more concern with this one, this portion. Okay, this is optional one. Thank you, students, very much. Assalamu alaikum.